Hello, everyone. This is Christine Perey, Chair of the AR for Enterprise Alliance Research Committee. Welcome to today's Area Research Committee webinar. I'm very, very pleased to have Jarrell Perey join us. It's September 19th, 2024, and the topic is one you may or may not be thinking about, but if you are deploying AR in an enterprise environment with wireless networking, you better be thinking about this soon. you may have already encountered it. So I'm going to invite Jarrell to introduce himself and his company. Thank you and welcome.
All right, thanks for that intro, Christine. Again, I'm Jarrell Perey. I'm a 6G technology specialist at Rohde and Schwarz, focused on extended reality, XR applications. And today, I'm going to be giving an overview to an approach where you can use wireless application testing to increase the overall robustness of enterprise AR applications. And for those that may not be familiar with Rohde and Schwarz, we're a company based in Munich, Germany. We're a global company with offices throughout the world. We have 3 divisions: test and measurement, serving the wireless industry, aerospace and defense, automotive. We have a technology systems division, which is inclusive of secure communications, such as radios, various types of critical network infrastructure, broadcast and media. And we have a networks and cybersecurity division. My role is in the test and measurement division, and in the presentation, we'll be referring to a few products produced by that division. I'll begin with a description of some of the challenges we see in constructing a testing setup that can adequately replicate the environment you'd expect for wireless AR applications in production or deployment. From there, I'll move to the description of a lab-based XR testbed approach to addressing those challenges. And then I'll just describe how you can use the testbed and the data it produces to optimize the end-to-end robustness of your application. I'll conclude by looking ahead and highlighting some interesting trends in academia, in the industry, that will impact AR wireless applications in the future. So the focus of our discussion is on AR applications that have wireless dependencies, that are wireless bound. And one of the most well-known examples of that type of XR architecture is remote rendering, which I'm sure some of you may be familiar with. That's depicted at a high level in this diagram, where on the right, we have a client application running on an XR device. This client application is relatively lightweight, and it sends controller input, sensor data, pose information, what the user is looking at, back to a remote server. That remote server uses that information to create an image or render an image of what the user is seeing, and then streams that down back to the client, effectively offloading the computationally heavy task of rendering, and, as you know, enabling with power savings, and ultimately this type of architecture, as we know, is expected to enable very lightweight XR and AR devices that can be used for long periods of time. With that distributed compute architecture in a testing, there can be many configurations of it. Different tasks in the application. Some may run on the device still, of course, but others, they can be located on a local private server in a private network on a factory floor, for example. It can be deployed to an edge compute node running close to a 5G network core. Our services can be deployed to the central cloud, to our hyperscalers, your Amazon Web Services, Microsoft Azure, Google Cloud Platform, or the Google Cloud Platform. Optimizing the data rate and the network latency for these types of applications obviously can be very challenging. Ericsson wrote a great article. They titled "Network Performance in the Metaverse: Can 5G Deliver What's Needed?" Where they showed an example of one of their AR test applications, and broke down all of its processing components, listed where the processing is taking place, either on the device or remote server, and listed the latencies, but not the network latencies, just the process completion latencies that are on the device or on the server. And as you can see, they're very significant. Just simultaneous localization and mapping. That task alone can take as long as 70 milliseconds. Object detection can take up to 250 milliseconds. So when you look at just the own server or own device latencies, you have very little budget left for your network induced latency. And if you're targeting the often cited 20 milliseconds end-to-end latency for comfort, for full remote rendering, or even the upper bounds of 100 milliseconds, you can see that you need an ability to do everything you can to optimize network latency. In building a test setup, you also have the challenge of replicating the various network technologies you're going to be using. And that could be a private 4G, 5G network, a public 4G, 5G network, Wi-Fi. You may also be using network slices within a 5G network. In addition to having the network technologies in place in your testing setup, you also need a way to manage the load, and also replicate RF interference conditions. On top of all of that, you may need to over the protocols like the low latency, low loss, scalable throughput. So one example of these device and application vendor features will be modem APIs where the application can communicate directly from the modem to get more accurate and more timely latency measurements. To address these challenges, one way to do it is to build a end-to-end test bed. And at Rohde and Schwarz, we have prototyped one, which is depicted here. The center of the center of this test bed is built around our network emulation components. And for us, we're using our Rohde and Schwarz CMX 500 5G one-box signaling tester, which can deliver a lab-based and a controllable 5G network and Wi-Fi network. And our ATS 1800C Shield box allows us to isolate our device under test, our headsets for the testing sessions. And within this chamber, we have used to date headsets that are fully integrated, that are not tethered to smartphone tethered headsets. We also have the ability to place a artificial head positioner that can be remotely controlled, that can simulate head movements. The network emulation components also have a very useful capability of connecting to external servers, again, that can be nearby, a local server, or again, as I mentioned, deployed on the edge or on the cloud. The test bed can accommodate a variety of distributed application architectures, ones where, say, you have a digital twin model that you want to render completely remotely in the cloud, or a interactive avatar where maybe you have a large language model running remotely and you're doing lightweight graphical rendering on the client. We can accommodate those. Also, our CMX 500 does have an embedded computer, so there are certain tasks within the limitations of its CPU that you can deploy there. So you have options. But a key point here I want to highlight is that when you think of traditional software development, you typically have a development environment. The developer has their own developer environment, and that today that's usually on the developer's laptop or a desktop computer. And then you have a staging environment that can be on a local a cluster on a local network, or a carved out section of a set of virtual machines at a hyperscaler. Then you have your actual production scale production environment. What this testing setup gives you, it amps up, it gives you new capabilities for the staging environment. It gives you a realistic networking technology within it, with the ability to emulate your 5G network, your 4G, 5G networks, Wi-Fi, and and simulate switching between the two. Another important capability of a test bed, which I think would be obvious for those of you that work extensively in software testing, is automation. And through this test bed, our prototype, we use software called CM Sequencer, which is referred to in the monitor screenshot, the monitor image there, that has some built-in tests for controlling our equipment, but it also has allows you to integrate Python scripts, which you could use in any test bed. And with the scripts, you could start and stop services on the remote servers. You could start and stop the client app, and it really gives you a very efficient way to generate the data you would need to analyze the performance of your application under different conditions. So once you have the test bed, you need an approach for using it. And here is a suggested workflow in which you could use this type of test bed to enhance the overall robustness of an enterprise AR application. The suggestion would be to start by introducing RF channel impairments that simulate different interference conditions. Do that, vary the traffic load, and while you're doing that, capture network KPIs. When you capture those KPIs, then you have the option of looking at them and then determining a way to assess the quality of experience. And I have a suggested pointer of a way you could do that. And then once you have a good indication or a good record of the QoE, you can start to strategize how you could address some issues and bottlenecks you may find in your end-to-end flow, make some decisions around server-side changes, networking protocol changes, or client-side changes you may want to make. So in your strategy of varying your RF and network, varying your RF conditions and your network load, a suggested strategy is to think of varying the RF conditions along ideal conditions, moderate conditions, and extreme conditions, but doing those in parallel with different combinations of the traffic load, from something you consider an unloaded network to a loaded network to a completely congested network where packets are being dropped. By doing multiple combinatorial possibilities, you can generate a great set of network KPIs you can work with. And again, this is review for many of you, I'm sure. Latency, data rate, and continuity, or overall end-to-end reliability, are your key network parameters for wireless AR and all XR applications. And as you know, latency in many cases and minimal jitter is sometimes more important than data rate. As we described with the test bed, you can dynamically vary these parameters, and then you want to measure them using your standard KPIs of RTT, packet round trip time, transmit time, receive time, and then packet delay variation, your packet error ratio. And the PDV will give you some indication of your jitter, which you do want to minimize for remote tasks like remote rendering. So now that you have your data, information on, you have your network KPIs, is you can look at the overall quality of experience or find a way to measure what would be the user's sense of perceived satisfaction. And one interesting way to address that is by looking at a recommendation from the International Telecommunications Union, which describes a methodology that quantifies the relationship between network metrics and the application's QoE. They have a document which you can view online, G1051. It describes an interactive test, and it shows it describes a mathematical relationship between these factors and QoE. To use it, first you have to capture traffic patterns by analyzing traffic in the application. And on the right, you see an image from their recommendation document that shows a traffic pattern for an interactive remote meeting. As you can see, over time, you have a spike in uplink traffic, which could be, for example, sharing a document, then a spike in downlink traffic, which could be a shared document from another party, or it could be a video conversation coming in from another party. But once you capture those patterns and you play them back across their different network conditions, you want to capture all of those KPIs we mentioned: RTT, PDV, PER. And their recommendation and the recommendation document suggest capturing them using a server technology called the two-way application measurement protocol, or as a responder or reflector. You could set that up on the server side of your test bed, and then on the client side, you could play back the traffic, or if you can reliably reproduce it, reproduce the behavior. So you send those packets across, you capture your metrics, and then you apply them to an interesting interactivity model they built. And the scoring and the model, the model is shown at the bottom in the screen captured from this image captured from the document. And the model is based on the notion that there's a relationship between latency. It's a monotonic relationship between latency and perceived interactivity. So for example, lower latency will produce shorter application response times, which results in the application being perceived as more interactive and useful. So I think that's intuitive to many of us. So the more responsive, the snappier the application, the better experience you'll have. This just captures one aspect of QoE, just interactivity. And this model, you won't necessarily have to take it at face value. You can modify it to your needs. There's some research literature out there where you can see examples of other people doing this. To really utilize it, you really want to tweak some weighting factors. You see, A and B, alpha and beta in here. Those are different weighting factors that determine saturation points at which latency starts to impact interactivity, and also points at which latency is so bad that the application is completely not useful. So tweaking those parameters is really how you can leverage the power of this interactivity score. But with automation, you could take many of those combinatorial possibilities I described between RF interference and various traffic load conditions, and you can run multiple tests, get multiple runs of the interactivity score, and then develop an idea of where your bottlenecks may be. If you're suffering excessive packet loss is a problem, one thing to consider is leveraging the IETF's L4S protocol, low latency, low loss, scalable throughput profile. And this is a diagram from a Nokia Bell Labs article on it, which is a great introduction to it if you want to learn more. But essentially, instead of dropping packets during network congestion, the packets are marked. You start to get markers for ECN markers, explicit congestion notification markers. And once the client starts to receive those, the client can start communicating with the server and saying, slow down. And through that tight coordination, you can prevent packets aren't dropped, and you can effectively maximize throughput while minimizing latency. This protocol, there's support for it built in some of the popular remote rendering systems out there today, and I will say that it can be very effective. I've seen some very impressive results during less than ideal conditions, and I was surprised by the positive impact it can introduce to an end-to-end system. Well, looking ahead, and as we know, quality of experience is very subjective. It's typically evaluated using questionnaires, mean opinion scores, and VR. Often we use there's the standard presence questionnaire, but the International Telecommunications Union started looking at this, and they began by enumerating what are the factors They first looked at virtual reality with their G1035 report, and they're all, when you review that, it's, it has some of the obvious factors, cyber sickness, minimizing motion to photon latency, those type of factors. And then, more relevant to our discussion, with their 1036 report, they focused on augmented reality QoE factors. And here we have a screenshot of the ones how they broke it down. And they broke it down into quality of presentation, quality of integration, quality of interaction. Presentation covers things like video resolution, integration, as factors such as tracking performance. They have lighting performance in there, and then interaction quality, which is related to some of the our discussion with the interactivity score and speech performance, gesture performance. But these are just these are nice list of factors that industry forums are coming to consensus on. The work going on today is to come to an agreement on what are the best ways to measure these factors. And I think that's going to have a lot of impact on our work, or those of us working to optimize end-to-end from an end-to-end perspective, AR wireless applications. There's also a growing body of work in academia where ML, machine learning models, are being built that can be used to predict quality of experience, where they can say, for example, okay, here's a set of network conditions, and maybe here's a set of pre-existing conditions. Given those conditions, what could we expect the QoE could be? That can have some utility. Particularly, you could imagine having a QoE model built into your application where you could start to proactively respond to conditions based on a model that you found to be sufficiently accurate. But moving beyond industry work or work to gain consensus on quality of experience factors, moving to measurement, 3GPP, the third generation partnership project, for those not familiar, that defined the 3G standard, 3G specification, 4G specification, and 5G. As part of their recent release 18, finalized earlier this year, they released a technical report on suggested metrics for AR and MR services. And this is a screenshot and of a table in the conclusion section of the report that lists the metrics that they think have the best chance of being able that are most appropriate for developing measurement methodologies. And the thing that you may find useful for practitioners out there and developers is that it provides suggestions on how to measure them using the using OpenXR API calls. There are sequence diagrams in there. So if you're looking at building some QoE measurement tools, this document is a good resource, or at least a good starting point as the industry continues its efforts in this space. Another trend that we're seeing, particularly with the latest release of 5G, with 18, which is referred to as 5G Advanced, and the discussions that we're having that are being held in industry forums around what 6G will be, which is expected from a commercial perspective in the 2030s, is this concept of the network not simply being a communication network. You're seeing terms such as network application symbiosis and integrated computing and communications. And that comes down to the fact that today a network does not have much visibility or the ability to adapt to the needs of specific applications. So, for example, let's say you have on a network an XR application running on the network, YouTube, someone viewing a YouTube video. All of those are treated equally. There are QoS settings in the network, like QCI levels, but it's a heavy lift to change those. So one feature, part of 5G Advanced, is PDU set-based QoE handling. And with what that enables is to set QoS parameters, not just for individual packets, but group of packets called PDU sets. An entire PDU set can encompass, say, an entire video frame instead of part of it. So let's say you have a remote rendering application. It's very important for your frames. You don't want to drop any frames to guarantee user comfort. So by prioritizing groups of packets, you can see here in this diagram from Nokia, the high importance sets are green, the lower importance sets are blue. And once the packets reach the cellular network determines, either due to congestion or even maybe power savings needs, it can discard the less important packets, the blue packets that wouldn't be the video frames, and make sure that no matter what, those remote rendered frames make it down to the app. So these type of capabilities really make the network more aware of it, can make the network more aware of XR applications and adapt on the fly, which will be very important, because we all know network conditions, they're not always guaranteed. They can vary widely, and we need all the tools we can possibly have to allow the application and the network to adapt. There's also another feature which allows the individual applications to report back to the network and say, hey, I'm this AR application, and here are the metrics I'm getting, and you can, and the network can respond appropriately. Also, for those that aren't familiar with the 3GPP 5G releases and support for XR, as a quick overview, the initial releases of 5G, which began with 15 and 16, they focused on network enhancements, focused on power efficiency, enhanced mobile broadband, which is that increased speed we see with 5G, and ultra reliable low latency communication. All of those things weren't built directly for XR, but they can benefit it. But starting in 17, there was a technical release 17. There was a technical report looking at what needs to change in the 5G system, what to improve XR applications. And in 18, we started to see specifications for the first features dedicated to XR. Many of them related to making the network more aware of the application, like we just discussed, scheduling enhancements, and power saving features such as connected mode, discontinuous reception. But I would refer you to the 3GP documents and some of their articles that summarize these for more details on all of these features. Release 19, which is currently in progress, builds upon those Release 18 enhancements, but also moves into a new area with support for multimodal streams, which is really interesting, which is depicted in this in the bottom right here from an image from one of the technical reports, where you can have dedicated QoS parameters for, say, a tactile haptic data, a separate stream with its own QoS parameters for gesture data, a separate one for 3D audio conferencing data. And you can set different parameters for those. And then also the network has capabilities to synchronize those. So again, that'll be another tool to allow the application to be more tightly integrated with the network and allow both the network and application to adapt to maximize QoE. So in summary, a test bed like the one we described can be very useful as long as it incorporates network emulation capabilities, and it can be a very important tool for increasing the overall robustness of an enterprise AR application. The data that it produces can be utilized to find key issues in your impacting quality of experience, and assist in developing a strategy and action plan for optimizing your application from the end to end, from the server side all the way down to the client. And the development of our test bed we're doing at Rohde and Schwarz is a journey. It's evolving. We've just begun, and we certainly welcome your input and feedback. So thank you all for your time today. Are there any questions?
That was just excellent. I want to congratulate you for using the time that you had perfectly, but also I liked how you spent an appropriate amount of time talking about the future, because what we have today is just the beginning, and a lot of people, can better plan if they can see what's coming, and so that's really valuable. Also, I really like that you included so many links to important documents and standards, not necessarily new, 2022. Those are, that's how things work. We have to get the word out. If people create excellent documents and do fundamental or even applied research, but it doesn't reach its target audiences, it doesn't have the impact that it could have. So I want to thank you for that. So the one question that was brought up, but I think you answered it quite well, was, how is the traffic from an enterprise AR application different from any other low latency applications? I thought at least the last 5+ minutes where you were talking about the different attributes and quality of experience, those are perhaps I could let you answer the question instead of me saying what you already said.
Well, I think, in an enterprise application, many, and this is my opinion, they view it as a more controlled environment, and that may not necessarily always be the case in practice. In those environments, you may also, if you have the advantage of an ideal situation today where you have a private 5G network, you may have the capability to support network slicing. And in that, in your testing setup, you need to set up those slices. Our prototype test bed does support that. But also, I think enterprise environments, they can be very complicated. I would say, more congested, denser. There may be more sources of interference than you would have in a wide area public network. So, from a test bed perspective, the RF interference testing could be critical. You would want to avoid the situation where you conduct all your development on the developer's laptop, and you test primarily on a Wi-Fi network under standard conditions, and then you put it out on, say, a factory floor. Then all of a sudden you're dealing with interference from some unexpected sources and areas. You want to be able to
big blocks of metal, big bodies of water, things like that.
So these things, so your environment can get more. There are aspects of it that can be more advantageous versus a public network, like having access to private network slices. But because it's a very dense environment with potentially more unpredictable sources of interference or things you wouldn't see in a public environment, things can get more complicated. So there's things that simplify it, but the good thing is a test bed approach, you can mitigate those challenges, particularly I think on the RF interference side.
Excellent. So, I think our area human factors committee probably talks a lot about quality of experience assessment methods. I know for a fact that the human factors team talks about those and considers them very highly. If we were interested in further studying the QoS assessment methods, what are other resources or starting points that you use or that you could suggest to our committees and to our members?
Yeah, right. And I wouldn't say that I have presented a comprehensive survey of XR/QoE by any stretch of the imagination here, but starting points I would suggest and that I'm using. First, I look at the ITU documents. All of these are readily available, publicly available. There's the ITU interactivity test, and there's great information about that and information on how to implement it. There's information on, I mentioned the two-way application measurement protocol. That is an established protocol. You can find information about that and sample code or servers that may already have it built in.
Right.
There are other ITU has other some interactivity tests work out there. There's some interesting work around cloud gaming QoE testing. There's sample code out there for that. So depending on your application, you may find that to be useful in conjunction with the interactivity test. I would also refer you to that 3GPP AR/MR document that has some guidance on collecting metrics specific to AR. One of the things that I found a bit challenging when looking at augmented reality applications is that a lot of the initial work done in this field is focused on virtual reality, and it's particularly focused on immersive video streaming, 360 video streaming, 180-degree video streaming. And that makes a lot of sense because it's a very accessible use case, and it builds directly off of existing quality of experience methods that are very robust, that are built for, say, analyzing YouTube video quality of experience,
or television, even before that.
And
decades.
And some of you may be familiar with the ITU standards on video, and our test bed is used for that and supports those standards. So it was natural to see that. So the AR work is newer, but it's exciting to see some consensus coming together on how to measure it. And I think some of the more exciting stuff is around how you can build QoE models, ML models for predicting QoE, and how we might be able to use those in applications. That being said, academic papers, I think many of us may just go straight to Google searches. Sure, that's a useful. But in terms of conferences that I go to, conference publications, IEEE, ISMAR, the International Symposium on Mixed and Augmented Reality. There's great literature there. And again, as Christine pointed to, some of the useful literature may not be new. It may be further back, but there's I think ISMAR, the publications go back close to 25 years.
Yeah, that's right.
And then IEEE VR, the conference also has some AR papers, and that conference has some good body of work. But for those of us that don't have aren't in more of an R&D mode where we can build up, with these industry standardization efforts, hopefully we'll have some prepackaged solutions for this. And like we have today for video quality testing, and for the ITU interactivity test, Rohde and Schwarz has a prepackaged solution for using that. So the good thing is these standards, they do have a history, or these recommendations from ITU have a history of being built into products. So
yes.
Yeah.
I remember, 15 plus years ago, the wave of research, probably was 20, talking about objective quality measurement, because up before that, it was always subjective, and there were people called the video eyes, and they had trained their brains. But when it became possible to use computers, it was like, oh, this is now objective to measure these parameters. I thought it was very helpful. One of the tables that you used showed all the parameters, such as, gesture interactions. I saw you waving your hands, I'm waving mine. We know how fundamental and how precise hand gestures can be, and the speed with which we use our facial expressions and our hands to do our work, right, every day. Yes. So excellent. So, I think it's always intriguing. And I know, Jarrell, you've been in this field as a very long time. I don't want to age you, but don't want to date you. But as we work towards lighter wearable devices, untethered. I mean, I see a lot of companies still using tethered devices, usually to some type of a portable, a smartphone. But as we go further and further towards lighter weight and new device characteristics, they haven't been introduced yet. See you next year, and the year after that, and the year after that. How can those who are working on the hardware, better use these test beds? You focused appropriately for the area on how can customers and solution providers, systems integrators, how can they use a test bed to better understand these conditions? But now let's focus a little bit on this, dwindling number of companies. Hopefully there's hundreds of companies coming out with new lighter weight displays. How can they use a test bed to optimize and to work on their future hardware?
Right. Now, I think this is a great question, a forward-looking question. As many of us know, to get to these lighter weight headsets, one path to that, or our key path, or from some people's opinions, the essential and only path is more computational offload. And I discussed some of that earlier in the presentation.
Yes.
That, today we mainly see it, particularly in some enterprise applications. Just remote rendering. You have a very complex model that there's no way it could render on a Meta Quest. You offload that to a local server with a powerful GPU. But moving beyond that use case, where more akin to what you see with that Ericsson article example, where you take all of your application components and you move some of them to different remote locations, you keep some of those on the device. You really need a test bed to determine what you can keep on your device and what you can move away, and the impact of that, the impact on battery life, the impact on heat. Because say object detection alone, you may find that on the device consumes 40% of your battery life. Maybe you need to move that over and to make those trade-offs.
Change
but
the
also,
like as we're getting to Gaussian splatting, there's more and more discussion about how to use that to model the 3D environment, but it is not computationally free.
Right. And the interesting thing, that's a great point you brought up there, because we're starting, and I didn't mention this but the emerging trend is, the merger of our AR application space and bringing in AI capabilities. And I think for those, we're seeing great examples of that. We saw that with, Snap had some nice demos of that, live demos this week, and who knows, we may see more of that next week with Meta's announcements. But yeah, those have computational load. But another thing that you'll want to be able to do beyond just saying, let's put this on the server, let's put this, on the device, is to switch between the two. Because let's go back to the standard example of remote rendering. Let's imagine that, you have a condition, you're on a mobile network. You may want to have the capability to switch between local rendering and remote rendering dynamically and smoothly. And the test bed, and the term dynamic distributed compute, you're starting to see that in technical marketing literature for it. But I think to really utilize that capability and to do it well and to maximize the battery life and long-term
and deliver the quality of
times,
experience.
And to maximize that QoE, you're going to need a test bed. You're going to need a test bed to induce those switches and determine, what can determine those thresholds. They can't be guessed at.
As much as we want to.
Yeah, we don't. Yeah, I mean, as from a developer, for those, with the developer hat on, you want to be finished and trust that it works. But with these distributed architectures, testing is going to become even more critical, because there's just too many variables out there, and adaptation. The adaptation's the word, and
right.
We have a great history.
Yeah, that's adaptation to the conditions of the moment, and that user. Just I think of cases where users are walking through very, very dense spaces, but if their purpose is just to get from A to B, then we don't need to analyze all the dimensions, and we just need to present them with the very minimal information to get to their destination, whatever that that extra piece of material is, or where that equipment is that they need to inspect, and not necessarily. So this is kind of a use case fluctuation while the person is in motion.
Yeah, and I think, we go, there's some terms, from other parts of software development history and I guess media technology history that are useful here. We talk about graceful degradation. I think that's, a QoE objective we can optimize for with a test bed approach. We also, you can think of the analogy, the development of video streaming technology. We used to be able, in earlier days, we would see buffering, we would see, blocky artifacts appear. But what's happened is, we developed adaptive protocols that actively monitor the network and switch between video resolutions and bit rates, to the point that the quality of experience these days, even under very, very bad conditions, is pretty good. And but looking at our challenge in our space, we have a much bigger challenge. We're not just dealing with one media or sensory stream. We may have multiple ones. They're going to vary on an application-based use case. Fortunately, 3GPP is really looking ahead. You saw that work I mentioned with multimodal stream synchronization, and multimodal QoS. That's what it's going to take. But those are just specifications. Christine mentioned how old some of those those documents were, and part of that is maybe due to dissemination, but the other part is it just takes a long time to get industry agreement on the specification, and then there's a period of time
implement
to build it. You have to build it
in the hardware to build it. Yes, I know.
Right.
And then you get things like, let's see, in 2023, AI just took off, and the resources that may have been focused in one area get diverted. Let's just use a nice word for it, diverted. But it's always good to see, the focus that you bring to your research and to the projects that you do, Jarrell. I hope we'll see each other at ISMAR in Bellevue in a month. And if not, we'll see each other online in the future. Thank you for your time today and this excellent webinar.
And Christine, thanks so much for the opportunity. Really appreciate to present to everyone today. And again, I look forward to interacting more. Thank you. Thank you all. Thank you for attending.
Thanks a lot. Bye-bye now.